Hello everyone, welcome to the Aeromechanology channel. Today's topic is an introduction to sheet metal design. Sheet metal design involves creating parts from thin, flat metal stock by cutting, bending, and assembling processes. Industries include automotive, aerospace, electronics, construction, and more. The importance lies in being cost-effective, lightweight, and offering high strength. Properties of sheet metal include materials used, such as steel, which can be cold rolled, or stainless aluminum, brass, copper, and titanium. Thickness typically ranges from 0.5 millimeters to 6 millimeters. Yield strength and ductility are important properties for forming. Surface finish is a consideration for aesthetics and corrosion resistance. Key design considerations include several important factors. Material selection is crucial based on strength, corrosion resistance, and cost. Bend allowance and relief ensure proper material flow during bending. The K factor describes the neutral axis in bending. Minimum bend radius prevents cracking. Tolerance considerations account for material and process variations, and design for manufacturability, or DFM, optimizes the design for ease of manufacturing. When it comes to sheet metal processes, there are a few key methods to consider. Cutting can be done through laser cutting, water jet cutting, plasma cutting, and punching. Bending involves techniques like press brake bending, roll bending, and edge bending. For joining, we have welding, riveting, screwing, and adhesive bonding. Common tools and software play a vital role in sheet metal design and fabrication. Tools include press brakes, shears, punches, bending machines, and welding tools. On the software side, CAD tools like SolidWorks, AutoCAD, CATIA, and Siemens NX are essential. CAM tools such as Fusion 360, Inventor CAM, and Edge CAM are used for computer-aided manufacturing. FEA tools like ANSYS and ABAX are crucial for analyzing stresses and deformations. So, let's talk about the advantages of sheet metal design. First up, high strength. Even at thin dimensions, sheet metal maintains its integrity and durability. Next, versatility. Sheet metal can be cut, bent, and joined into various shapes, making it incredibly adaptable for different applications. Scalability is another key advantage. Whether you're working on a prototype or mass production, sheet metal is ideal for both scenarios. Then there's the lightweight nature of sheet metal. This makes it perfect for industries that need to save on weight without compromising on strength. And finally, recyclability. Metal can be reused, supporting sustainability and reducing waste. So, those are some of the top benefits that make sheet metal design so valuable. Applications of sheet metal. Automotive components include body panels and frames. In aerospace, sheet metal is used for fuselage, wings, and structural parts. For electronics, it's used in enclosures and brackets. In construction, it finds applications in roofing, gutters, and HVAC components. And finally, in furniture, Sheet metal is used for cabinets and shelving. Design best practices. Minimize bends to reduce cost and complexity. Use standard hole sizes to align with available punch tooling. Avoid sharp corners to prevent cracking during bending. Maintain uniform thickness to avoid unnecessary material variations. Allow for tolerances to account for manufacturing variation. Utilize reinforcing ribs to add strength without additional material. Design for manufacturability or DFM. Standardize design elements by using common features across designs. Limit complex geometries to reduce production time and cost. Ensure material usage efficiency to minimize scrap. And simplify fastener selection by using a limited range of fasteners. In conclusion, sheet metal design offers strength, versatility, and scalability for a range of industries. Always consider material properties, process limitations, and design for manufacturability. Thanks for watching. Please like, share, and subscribe. Happy learning.